Hello grade 12s, welcome to my channel. Let us try to work through the geometric series and see what we can gather from just exploring it a bit, using some basic approaches, and then try to refine it using some standard approaches. Okay, now we need to consider this series, which we've got 2 going to 4 to 8 to 16 to 32. And we can see that we are just multiplying each term by 2 to get to the next. So our common ratio here, is 2. Alright, so this is a geometric series. Great. But again, we were told what it is, so we don't have to stress about it. Now this is very easy because it's short. A shorter one we can solve easily. So we know that we call it S sub n or Sn, but make sure that the n is smaller than the s, okay? Great, because it's a subscript. So this is 2 plus 4 plus 8 plus 16 plus 32. Now this is as good as just adding these terms nicely. So if we add this strategically, we get 10, right? And we add these 2 strategically, we get 20. That's 30. 30 plus 32, we get 62. So that's it. Easy. But now this is very easy and possible when we have a shorter series. Okay? So as a student, I used to like to look at maybe somewhat a longer series, longer sequence. I would just cut it short and study the shorter version. Then take the pattern into the longer version and solve the problem. So now when we have a shorter little version, let's try and play a trick on it so that we can see what to do when we have a longer one where we don't even know what the other terms are in between. But how would we know we can forget about them? Now let's propose another smarter way. Now this was a way proposed by a particular student to a particular professor's question when this thing was long, because from there we started to develop ways in which we can standardize how to handle this problem. Anyway, let's see. This student decided I'm going to have S sub n as the original series. Okay, and then decided that since I could see that I have a common ratio of 2, what happens when I multiply 2 to each term of the series? When I multiply the first term, I get the 4th term. Obviously, there's nothing here, right? Right, and then plus. When we multiply each term here, we get this term. So we align the ones that look alike. So what we're doing here, we're just multiplying that first term with 2, we get the second term. But we write it underneath the second term strategically. So again, we go for the second, it gives us this term. And then strategically, we put it under the third. Then we go for the third, we get that 4th term. But strategically, we place it underneath that one. And then we will get this, but we'll have an extra term. 32 by 2, that's 64. Now the student is like, okay, all right. Now I want to get rid of things I don't want because they confuse me. They make my mind sweat. Decided to put a negative, meaning equation 2 minus equation 1. Now this is 2 S sub n minus S sub n equals 0 minus 2, it's minus 2. Right, in fact, don't write anything here. Just leave it like this so that we don't get confused. Then we know 4 minus 4, See, this is where the magic happens. The magic happens here. You see, the magic happens here. This is what the student created. So the reason why all the troubles is because we want to get rid of these terms so that we never have to worry about them. So do you see what happens here? We get 0, 0, 0, 0 plus 64. So this implies 2s sub n minus s sub n is just going to be s sub n equals, now 64 minus 2, what do we get? 62. Very easy. Can you see? We're getting the same answer. But this is a smarter way to handle a much longer series so that we don't perform a complex operation, a very tiring and lengthy operation. So these are some of the things, guys. I know these things are not necessarily examined like this at times, but I can tell you it's a scam to tell you this thing is not examinable. So don't think it's just something to watch and not care about. It's gonna come to haunt you, believe me. You have seen how so random questions can come sometimes in the exam, and they require this very thing that people neglect. Take the derivation of the arithmetic series formula. No, the geometric sequence formula. If you look at that, that was the 1.3 in the November 2024 exams. Maths paper 1, 1.3 was exactly that. But you didn't know. Some of you didn't, because you always pass that proof in the textbook. And it's not there just for decorating the textbook. It's there to give you the reason why things are the way they are, so that you can see beyond just what you're given. All right. Of course, another student may be very silly and say, look, man, you are bullying us now. Why are you choosing the second equation? What happens when I take the first equation instead? What happens when I say s sub n minus 2 s sub n? We will get 2 plus 0 plus 0 plus 0. This time it's going to be minus 64, right? And what is this? It's going to be minus s sub n equals minus 62, sorry. Because minus 64 plus 2, sign of the bigger number prevails. Then we just multiply by minus 1 throughout. What do we get? S sub n is 62. So it doesn't matter which one you take from the other. We end up with the same result. Okay, so this is very important, guys. So as I said, I often did this. Looked at a smaller version of a sequence, see what I will see, then transfer that pattern to a much bigger one. Because if it fits a certain pattern, then there's nothing to worry about. So these tricks are very important. So let's take a worked example just to highlight this fact. Now here is a series to consider. First of all, nobody tells us what the series is, but we know that we're dealing with a geometric series, at least for now, but in the exam you wouldn't know. So we need to check what is going on. If we say 3 divided by 1, we get 3. We're taking the ratio here, not the difference. So we get a 3, and then we say 9 divided by 3, we still get a 3. 27 divided by 9, we still get a 3. So we know this is a geometric series with a common ratio of 3. So we don't care how many terms are there in between, what. We will just solve this thing just right. Since we have a technique, we must sort it out using that technique. Now we know, guys, we've got our s sub n, 1 plus 3 plus 9 plus 27 plus dash 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 plus 177,147 right there. Then we take the common ratio, we multiply to each term of the original series. What do we get? 1 times 3 gives us 3. We place it under a number that looks like it, and then we continue. We will have something like this, and then of course things will just keep happening. We don't care about the in-between. And then we know we're taking the last one and we're multiplying it by 2. Maybe this one might harass us a bit, but we can still do long multiplication. This is very easy because all we do, just multiply 3 to each individual letter here. That's what it is. All right. Okay. All right. So we get 531,441. So this, sorry guys, I'm making a mistake here. First of all, what is coming before will give me this term, so which is 177,147, and then this one becomes 531,441. So the very important thing to do here is to ensure that everything is in order. Okay, what is important is to make sure everything is in order. So we take a division, a negative, the difference of the two equations. So we can say 3s sub n minus Sn. What do we get? We get minus 1. The magic happens. 0, 0, 0. We know that we're going to still have 0. And then the last one is going to be 531,441. So this implies, now we will end up with 2s sub n equals, now this one minus 1 is just going to be 531,440. And so we divide by 2. What do we get? S sub n is, just divide that thing by 2. 531,440. It's an even number, so it will definitely divide 2. So I get 265,720. All right. So this looks all right. This looks all right. All right. It looks proper. It looks proper. It looks proper. So can you see, guys, a very difficult situation has been made easy by just using a particular trick. As long as we know the sequence or the series forms, or at least fits into a particular pattern, we just know that if we play this trick very well, we can go far. And again, guys, I'm showing you this thing not just to impress you or to waste your time. This is a learning point, because a challenging question can come from this. Believe me, in the exam, remember, anything can come as long as it's within your grasp. Question is, have you reached far enough into the bag to get everything there is in there for you? It's up to you. Anyway, so this is how we handle situations, guys, knowing what we know. But this time, this is still very crude. We want to standardize how to deal with this. Now, folks, at this stage, I think we are ready to do a derivation of the Sn formula for a geometric series. Let's go for it. Okay, guys, so the derivation of the S sub n formula for a geometric series. Mind you, this is examinable. You can be asked to reproduce this in the exam. Okay? Don't just learn it for just reproduction. Learn it to also apply it in a situation that may demand this. You know, in calculus, guys, sequences and series apply. I hope you understand. And I've shown you the example from a previous exam question paper from Gauteng, where many students freaked out because a whole lot of them didn't know what to do, I doubt if any one of them did it actually. But here's the problem. It's not learning things to understand enough to use them whenever they apply, irrespective of whether someone tells you to do that or not to do that. But you use it as a means to an end. If you have not reached that level with your knowledge, just know you are wasting your time through schooling. Because you don't just go to school so that you can reproduce for the teachers so that they can be happy and then you progress. But you yourself don't recognize the need to apply what you have and what you know whenever you can, irrespective of being prompted to do so. All right? So this is very important, guys. So going through these things, I mean, they are there in the book. You could easily have gone through that and just crammed it as it is. But you see, when you cram things, you sound smart, but you're actually not. Yes, some people can argue and say, but without cramming, you wouldn't remember enough to explore, enough to use, enough to then understand. Perhaps cramming comes before the understanding, and that's actually not true. It's not true. If you push for understanding, trust me, then cram it later, because some materials are technical in nature. It's easy to forget, but remember, when you have understood something, even from memory, when your memory is a bit fragmented, you know how to tie it back, you see. So again, hey guys, I'm just a human being, who has his own opinions. I may be wrong about a lot of things I say. In fact, I may be very erratic in what I say. But hey, this is just my take, and this is how I have used these things to at least push myself to the level that I find myself today, which is still, yet another stepping stone, because I'm looking to jump to yet another level. And I'll keep on trying until I can no longer do that, okay? But I've also been able to teach people the very same approaches, and I have seen them soar as high as the eagles, Soaring means less energy but still flying high, than to actually try and ascend when you're going to have to expend a whole lot of energy. And what if you fail? Okay guys, so we want to derive, and again we know that this is a geometric series with R as the common ratio, because if we try, we have seen the sequence. This is a geometric sequence. Series is just the sum. We know R is the common ratio, right? Because even if we take that and divide that, we will still be left with R as the common ratio. So that's the very important thing. So how about we say, here is the solution for the problem. Our solution, we're going to take our Sn, say A plus AR plus AR squared up until to the last term, A to the R n minus 1. Actually, this is incomplete, isn't it? And then what are we going to do? We will multiply the common ratio to each individual term of that series. So we can call this R as n equals, now when we multiply R here, we get the second term. So we want to put it here. So this is what is going to keep happening. And we don't care about the in-between until we get here, when we are going to get exactly the same term. Right, plus, now this one times R. Now this is the same as AR to the n times R to the minus 1 times R, which is this one, to the 1. Can you see these ones take each other off? So we end up with AR to the n. Okay, nice. Now we do exactly how we have been doing our business. Now we just take the difference. It's safer to take the second one and subtract that one. But you can still do this one minus this one. We'll still get to the same result. But of course, the equations may be slightly different. It doesn't really matter. It just says something about when to use which formula. Now let's look at this one. We're going to say R Sn minus Sn. Mind you, this is a subscript. Don't hear me read it carelessly. It is a subscript. So if it is a subscript, we usually say sub, whatever we see there. Anyway, we're going to have a, not a, but minus a, right, right. And then what are we doing here? We are going to take this one out. So these ones are going to give us zeros. Can you see? We no longer worry about this one. 0 plus we get this one. It's going to be AR to the n. Okay, so this implies, now guys, remember simplification is what we know. When we see a common factor, we take it out because our target is to find S sub n. And S sub n here is the common factor. So we factorize by taking out the highest common factor. So we continue, and then what do we see here? We only have what we have. So technically we can write here a r to the n minus a. And we can see a is the common factor here. So how about we factorize this thing? So we take a out, and this is what we end up with. I'm moving quick so that you can cry. All right, okay, so what do we see, guys? If we divide by this term, this isolates our S sub n. So it's going to be a into r to the n minus 1, all divided by r minus 1. This is the formula to calculate the sum of any number of terms in a geometric series. All right. Now what happens if we decided to take the top and subtract the bottom? Let's do it. What if we said, well, Sn is equal to a plus ar plus ar squared plus arn to the minus 1, and then we took our r as sub n, and then we got what we got. Okay, so of course I know many students like to ask such questions. Silly as they sound, they are very good questions. Now what do we get, guys? We will get S sub n minus r S sub n equals, it's going to be a plus 0 plus 0 plus 0 plus, is it a plus? No, it's going to be minus ar to the n. Again, we still have a common factor here. So what do we have? S sub n into 1 minus r, right, is equal to, now what do we have here? We have a minus ar to the n. But again, we see a is a common factor. How about we take it out? So it becomes 1 here, and then a is out. And then if we divide by what is on the right, we don't want it, we get a into 1 minus r to the n, all divided by 1 minus r. So this is the formula that we get. Okay, very nice. So again, this formula is not very different from that. It's just that there are certain special cases that help us to do this. So what is very important, guys, is that we use this formula when r is less than 1. This is the condition for using this formula. And we will use this formula when r is greater than 1, okay? That's what we're going to do. And remember, r cannot be 1 in these sequences or in this series for those to become geometric. R should not be 1. Nice and easy. All right, guys, so these are the two formulae that we aim to use when solving a question of the sum in a geometric series. Now, when r is greater than 1, we use this formula. When r is less than 1, we use this formula. Very important to know these two formulae. Either way, even if you forgot, you decided to use this formula when r is greater than 1, you will just have to readjust things, that's all. You will not have a problem. Even if you used that one, you will not have a problem. It's just that it can get a bit challenging for certain students to actually see the sense in these kinds of calculations, because some can simplify into some exponential expressions, and now it makes it difficult to progress if things were not set up nicely. But again, if you understand algebra, you should not have a problem. All right, folks, so now we need to take some worked examples so that we can apply our newly found jewels. You know, if you bought something nice at the stores, you know, over the weekend, you cannot wait to wear it at school or in town or in the society for people to see you looking sparkling. Now we found something out of playing a mathematical trick and so that we could solve a very long situation by just applying a very simple approach. And that very simple approach led us to finding a formula that is bulletproof. As long as we know when to apply it, then we can get as far as we want. Okay, let's take an example quickly. Okay guys, so here comes an example. Given the geometric series 9 plus 3 plus 1 plus dash dash, now the instruction is for us to calculate the sum of the first 7 terms of the series. Now here's what is important. We need to know the number of terms, right? So we want S7. Okay, that's easy. Again, we are told this is a geometric series, so we can actually find the common ratio nicely. So we can see the common ratio is 0.5 or a half. Okay, maybe let's do it on top. I mean, it doesn't matter where we do it. So this is the common ratio, which is it a half? No, it's a third. Sorry. Okay, so that's our common ratio. Very important. So let's do the solution. We know that, well, Sn is equal to A. Remember, R is less than 1. So it's going to be A into 1 minus R to the N. Okay, maybe let's make it square brackets for a particular reason. Divided by 1 minus R. This implies that S7, because we are told there's 7 terms here. Now A is the first term, this is 9, into 1 minus a third, all to the exponent 7. See why those square brackets had to come in? Exactly, but even if you didn't write it, you can still write them here when we're going to have yet another set of round brackets inside. This is 1 minus a third. We can even put it in brackets. Now all is left is to write it into the calculator. So S sub 7. Remember, this is a subscript. Must be smaller than the letter. Sometimes my writing is so terrible that you cannot tell the difference between those two. But hey, ibialo ntwena, ibialo. So galla ha o batla, o ka thola ha o batla, o ka nkwatela ha o batla, o ka komanya ntho e nngwe le e nngwe o e batlang, o ka etsa hohle. Empa o hlokomele he, ke ska o shapa. Hobane ke na le molamo wa ka nna. Ke a shapa bathong ba sa tsebeng dintho hore di etswa jwang, ba sa tsamayeng ka molao. Ke tla ba bontsha ntho e mpe. Alright guys, so this is the stories. Now if we're going to take this to 2 decimal places, which is the common way, this is the story right there, or to a single decimal place or whatever. But this is exactly what we get. So we can see, guys, that, okay, all right, okay. The geometric series could be looked at increasing, like we have been seeing above, like this was increasing. But we could still look at it decreasing, and we already see that it decreases when the common ratio is essentially a proper fraction. Remember, proper fraction. Okay, because this is grade 8 stuff, guys. Is it grade 8? No, man. The fractions is as a level as a proper one. As for B, yeah, because sub B, guys. And I tell what in second year. As for B, sub B, guys. Because it's a substandard lantolia. A, that's why I was talking sub B. Substandard A, substandard B. Then uqale ke ngoku standard 1. Yayifumana. Ndiyazi le nyaka bayenzayo but substandard 1 but ngo grade 1. What nonsense is that? Anyway, ibhanqike injalo lonto. So this is what we call a proper fraction. Now, guys, I mean, these are things you learn in grade 2. Yes, grade 2. This is a proper fraction. Khumbula kahle uMampohle wayendifundisa wayevela athi xa ubeke le ngenhla athi what type of a fraction leyana siyazi uba it's an improper because ayivumelekanga lento. Awukwazi uthatha umuntu omdala umbeke phezu komntwana, ngumntwana otete emntwini omdala, not the other way around, right? So, and as a result uthola uba xa uno-5/2 wayengafuni ibhale kanje, wayesithi you are not allowed, in fact we were not allowed to leave an improper fraction like this. You had to ask yourself, how many times does this go? 2 times. Remainder 1/2. Now this was better because uthatha le uyibeke ecaleni then ibe proper le fraction, so that umntwana angateti umuntu omdala. Uyafumana? Yeah, simqhawula inhloko lo muntu omdala. Simqhawula inhloko bese siyibeke enhlokweni yalwana ayitete then ayirhuqe le the rest. Then kulula kanjalo, isn't it? Yeah, that's the thing. So yeah, guys, you need to know the things, you need to know the things that must to be known, or else uzokhala izicimamlilo. Now, guys, what the hell are we going to do with this situation? We want to take another example. Let's take another one quickly before I waste your time. Okay, guys, so here's another example that we want to take and just enjoy a little bit. I'm not going to complicate this. You may need to do simultaneous equations along the way, but guess what? You already know this. I have shown you how this can be looked at. So we'll just deal with some past exam question papers and perhaps try to highlight those situations. So far, we just want to build the basics as nice as possible. First of all, guys, we need to know what the series is, right? Right. Of course, we will pretend we don't know. Now, here's the solution. Now, we are given here that the sum of 5 plus 15 plus 45 plus dash dash to n terms is 605. Now, we need to determine the value of n, meaning how many terms are in this series, therefore. So, we know that technically Sn is equal to 5 plus 15 plus 45. K plus dash 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 to n terms. Right. And we can see that R is going to be equal to 3. Right? Because 15 divided by 5 is 3. 45 by 15 is 3. So this is a geometric series with R equal to 3. So what do we know, guys? We know that our Sn is going to be equal to A. Remember, the formula must be written first. Now R is greater than 1. We're going to use this formula. Divided by 1 minus r. Write the formula first. Don't be in a hurry. What is the value of Sn? We are told it's 605. That's the value. So 605 is equal to A is 5. R is 3 to the exponent n minus 1. All divided by 1 minus 3. No, lying. I wrote this wrong. So this is r minus 1. So 3 minus 1. See, so easy to write these things wrongly. And it's not allowed. So let's simplify this a bit. Goodness. This is 605 equals 5 into 3 to the n minus 1 divided by 2, right? So this is over 1. Now it's much easier to cross multiply because we can't break that bracket not knowing what that 3 to the n is. So we will break it sequentially. So we multiply that by 2. What is this? Yo I calculator of words but you can do it by doing long multiplication in the head. So this is 1210 equals 5 into 3 to the n minus 1. I mean, a round bracket can do. We still divide by 5 here. What do we get? So I'm getting here 242 is equal to 3 to the n minus 1. Now I take 1 over and I will rearrange. 3 to the n is going to be, we transpose 1, there we get 243. Now the question is, can we express 243 as a power of base 3 to a particular exponent? Let's find out. So we're going to say 243 equals 243, and then what is the next one? Shift, fact. What do we get? So shift, fact, I get 3 to the exponent 5. Okay. Now we know that, okay, we can continue and say this is 3 to the exponent n equals 3 to the exponent 5. Now once the powers, remember the power is the whole thing. Once the powers are equal and they have the same bases, it means the exponents should be the same too. Otherwise, how else are they going to be equal? It wouldn't make sense, would it? So that's it. We were supposed to find the value of n. We got it. This is a side calculation. You don't show it, but you must know it. Alright guys, so this is essentially how to deal with this issue. Sometimes you may just need to calculate the sum. Sometimes you may have to calculate a term in the sequence, a particular term. Sometimes it's a number of terms given a particular sum. So there's many ways in which these questions can be asked, guys, but I'm not going to go to too much of them because it does not help. You understand? Now let's take another example and explore this example just a little bit. I don't want to keep this video for a very long time because here we just want to leave it at the basic level and just handle the past exam question papers a bit more rather than to sit too much onto this. Maybe we can spend an hour here, it's fine, but I don't want it to be longer than that, or at least too much longer than that. Okay guys, so here's another example that we want to explore. Now we are given a series 8 plus 4 plus 2 to n terms. Now our first job is to calculate S6. Okay, so let's handle the solutions. Ooh, it looks like I'm gonna run out of space. Now I'm going to do what I hate to do, but I have to do it. So we know that Sn is equal to A. Of course, this is a geometric sequence or geometric series. 4 divided by 8 is a half. 2 divided by 4 is a half, and so forth. So this is our common ratio, which is what we need. Okay, all right, okay. So we've got A into 1 minus r to the n over 2. Sorry, over 1 minus r. This is the formula. So we're going to just keep going here. 8 into 1 minus a half to the 6, all divided by 1 minus a half. So what do we get? So we have 8 into 1 minus a half to the exponent 6, all divided by 1 minus a half. So what I'm getting here is 15,75. Okay, great. Okay, so that's the first one. Now let's do S9. S9 is going to be 8 into 1 minus to the 9, all divided by 1 minus a half. Okay, so what do we get? So now on the calculator, just go and change the exponent because that's what I want to deal with. So what I'm getting here is 15,97 to 2 decimal places. And let's see, S57 is going to be 8 into 1 minus a half to the 57 divided by 1 minus a half. Okay, let us see. I'm getting 16. Now let's see, S100 is going to be 8 into 1 minus a half to the 100 divided by 1 minus a half. Okay, all right, we'll go and check. So it's nice once you've got the framework on the calculator. I'm still getting 16. Hehehehe. 201 is going to be 8 into 1 minus a half to the exponent 201 divided by 1 minus a half. Minus a half, what are we going to get? We are going to get something. Isinikezwe 16. Hey, i-10 ngoku yasiqhela kakubi ngoku. Isiqhela kakubi le nto. 10 into ezininzi kangaka zohluka ngoku. Okay, guys. So now this one, I wanted to highlight something with it. This was just there to highlight something. Now we can see, guys, that with this geometric series, first of all, r is less than 1. Okay? And so we chose the formula that we chose, which is this formula right here. to do our business. Okay? And we calculated the sum of the first 6 terms. It seemingly was approaching 16, right? Because this is greater than 15 significantly. But then once we hit 16 right here, our magic number, it just pretty much remained 16. Now this is what we call the sum to infinity. And this 16 is the exact sum to infinity, because this was approaching 16 when we added those earlier terms. But once we hit the 16, it just kept repeating. Of course, we could ask ourselves how many terms in the first place added up to 16. That's a story for another day. But we can see that technically we hit 16. And 16 becomes the sum to infinity, because no matter how many terms, as we increase closer to infinity, we just always get 16. So this example was just here to highlight the sum to infinity. So we call this the sum to infinity. Okay, we only talk about this in a geometric series where r is less than 1. And now this thing introduces yet another thing. It is only possible in a geometric series where r is less than 1 but must be greater than -1. Okay, so this is a very important condition also, that the sum to infinity, we need to know that we apply it in a geometric series where r is less than 1 but greater than -1. And this half exactly highlights that fact. Alright guys, so this is the story that we can talk about. Now, let's look at how do we derive the formula for the sum to infinity. Iza kanjani? Iza kanjani? Okay, now let's have a look here. Okay, now guys, here's what we need to appreciate here. We are saying this only happens in a geometric series, number 1, where the common ratio must be less than 1, greater than -1. This is a very important constraint, guys. Please do not forget this thing. So how are we going to deal with this? Well, we know that when Sn, when we want the sum of the first n terms, it's going to be 1 minus r to the n all over 1 minus r. Why am I choosing this formula? Because already, for us to be talking about this, r is somewhat less than 1. But in any case, we know now that it has to be greater than -1. The greater than -1, we don't really care. The fact that r is less than -1, is less than 1, means this is the formula we want to use. Now this implies that s to infinity is going to be a 1 minus r infinity to the exponent infinity, of course, divided by 1 minus r. Now let's look at r. R, by being here, it means is a proper fraction. Remember that. It's a proper fraction. That's the thing. So that constraint, it means r is a proper fraction. that is between 1 and minus 1. Now a proper fraction, let's take, for example, 1 over 2. Now remember, this is to the exponent n. Now if we're saying we're getting closer to infinity, let's just take an example, 1 over 2 to the 1, and then we compare this with 1 over 2 squared. We compare this to 1 over 2 cubed, and we compare this to 1 over 2 to the 57, for example. We just want to check. This is 0, 0.5, right? Right. And then this is 0, 0.25, right? Right. This one is 0, awungiyeke mina phela. Akukho lutho zakungenza lona. Konje thina ndisazama ubala ke tana. This is 1 over 8. 8 to 1 goes 0 times. 0, 8 to 10 goes once, remainder 2. Then 8 to what 2 times. So izoba ngubani? Ku 0, 1, 2. And then remainder 4, right? Then C2 0, 8 to 40 goes 5 times. So this is 0, 1 to 5, ne? How to see confirm with calculator. Singekapha easy. You know what? It's easy, guys, to mess up, you know. Yeah, 0, 125. Now let's have a look at this one. This one, I don't want to think about it. I'm just gonna plug it. This is bad. This is 6, 9 times 10 to the minus 18. So this tells us there's lots of zeros here. This is 0, 0,0000, and then there's a 6 somewhere along the way as the first digit, and then everything else. But there's going to be about 18 zeros after the decimal before we hit that 6. You get it? Yeah. In fact, there's gonna be, let's see, by 18 but we need to push this one this side. When we push it this side, this decreases further. Yeah, there's gonna be 18 of them before we can do things. See, that one is a very small number. So in essence, guys, as the exponent draws closer to infinity, this whole thing becomes closer to 0, because we can see this becomes 0, 0.00006999 You get it? So this is the story there. This is the story. So can you see, this is just getting closer to 0. So this means if we've got r to infinity, when r is a proper fraction, it therefore means this thing is as good as 0. This implies that sum to infinity is going to be a into 1 minus r to the 0. Wait, so that thing is just 0, guys. Sengifuna ukuba namanga manje. Okay, maybe we don't need the big brackets like this. So this is a into 1 minus 0, because r closer to infinity, when we know that r is a proper fraction, doesn't matter what is here. R could be 1 over 10, could be 1 over 3, could be 1 over 6, whatever, as long as it's a proper fraction like so. Because anything that is less than 1, greater than 0, we know that it's a proper fraction where 1 is on the numerator. But that could be another story. Think, for example, let's say 2 over 3. Let me not say where the numerator is 1, because now maybe I'm over generalizing. What is 2 over 3 actually? 2 over 3 is 0.66666. So this also holds because it's a proper fraction. Let's just keep it at this being a proper fraction and stop the nonsense here, because I'm talking nonsense now. So as long as this is a proper fraction, it doesn't mean 1 has to be on the numerator, but a proper fraction that is going to be in this category. Less than 1, greater than -1. Okay, so as we continue with our business, we know that we have 1 minus r here. Now we therefore simplify the bracket. This is going to be a times 1, because 1 minus 0 is 1. A times 1 is just a over 1 minus r. Okay, all right, okay. So what do we say now? This is the formula to calculate the sum to infinity in a geometric series. But now, what type of a geometric series is this when r is a proper fraction? We call it a convergent geometric series. Okay, this is what we call a convergent geometric series. As soon as r fits this parameter of being a proper fraction between 1 and -1, we call that geometric series a convergent geometric series, and that means we can calculate the sum to infinity. This only applies when r is less than 1, greater than -1. Please remember that restriction, it's golden. Okay, so I'm sure you guys understand what's going on. Okay, maybe let's leave some of the stuff here, because we were trying to explain a thing here. These were just possibilities, and we were just trying to see, and now we can say therefore r to infinity is as good as it tends to 0, right? That's the idea. R to infinity tends to 0. This means it converges at 0. Hence, we put the 0 there. Hope you understand, guys. So this whole thing is a logical thing, guys. Okay, maybe not necessarily a logical thing, but we can display it so that you can see it. So some things you need to be in that position to explore them, because you may have seen this for the first time somewhere in your exams if nobody ever cared to explore it, or at least to highlight this to you. But I'm sure you all have gone through this, because no teacher leaves this part of, the geometric series unattended. So it seems to be something that we can appreciate. Okay, guys, not a problem. This is essentially the formula. That's what was important. Of course, be in the habit of knowing how we got to where we find ourselves, because it's easy to cram this formula and we can use it every time, but if we didn't understand even how did it come about, this is a problem, because a question somewhere in 1.3 or 1.4 or 1.5, but those kinds of questions, if they come and they have this content in them and you did not understand it, you will not be able to solve those questions. Thank God, it's usually just one question. So throwing away those marks is not that bad, is it? But it is bad if you are fighting for survival, because knowing how to solve that question might just give you a pass instead of a fail. By just understanding how to answer that question, you might just get a decent mark, like a 60% instead of a 58. In fact, by understanding how to solve that question, you might just get a 70% instead of a 69. In fact, by knowing how to answer that question, you might just get yourself a distinction instead of getting a 78. In fact, by understanding and knowing how to solve that question, just that question and not others, you might just get yourself 100% instead of a 98%. You get it? So folks, don't take anything for granted. It can be a huge difference when it really matters, okay? As much as it doesn't seem to matter for someone who already has a distinction anyway. But remember, the competition is getting a whole lot tighter now to get to university for a particular degree. And of course, the most popular degrees are very highly competitive, especially those that give you a job that pays. So be very careful, know how to get the work done, and just do it. Sometimes take simple examples like these and play with them. Take simple examples like that and play with them, and after playing with them, you will start to understand what's cooking. And the moment you understand what's cooking, then you start cooking. You just start cooking in the kitchen. All right, guys, I think I am done here, but I just want to take two nice examples so that we can see where does this apply, because we've already seen that we could actually do the sum to infinity here directly and say this is going to be a over 1 minus r, where we can say this is 8 over 1 minus a half. This is nothing but 16. So we could actually show it there. I'm just moving quickly now, guys, not to waste time, because I don't have time to keep asking you guys to calculate the sum to infinity. This is very easy. So it's usually a very easy question when it is direct, but usually in the exams this doesn't come as direct as you would wish. It usually comes in an indirect fashion. But hey, let's look for an example, maybe two examples to apply. I would rather we apply it, because this is usually how this is asked rather than directly at times. Actually, another thing before we move on, if we can just show the graph of the sum to infinity, on a Cartesian plane of some sort, where we say this is n terms, this is the sum, and we saw that the sum of the first 6 terms, of course, if we say s is 1, s1 is just the first term, so it's going to be 8. So this is what we're going to have right there. Then let's jump ahead and say this is S6. S6 gave us 15,75. Let's say this is 15 right here. So 15,75 would be somewhere around 16 if we wanted. And then we said S57, okay, maybe not S57 per se, S9. Also, it was closer to 16. And then we can just say this is 16 perhaps. But my S9 looks like it's almost there, not there, not there yet. S9 is just in there. And we could see that essentially this approaches a particular line. If we say this is S57, so it reaches the 16 mark, so to speak. So we're already there. And everything before is just trying to get as close as possible to. And we can see that we can look at that as the sum to infinity. Okay, guys, so that means the sum is more like a, think about it, what graph is that? Typically, it's more like a logarithmic graph.
What is it?
Oops, the TV is playing, okay. There was a power cut, now it came back, and the damn thing is just playing before I can play it. Anyway, if we were to connect the dots, we would see something like a log graph, so to speak. So sometimes you would understand why the logarithmic model, or what you call, something like that, is sometimes used when we are calculating certain things. There are certain things that just go to a particular number and never leave. So those functions, when we look at them, if we can put them as a function, of a particular variable, in this case n, for Sn, we see something like that. So hence those kinds of things can work, or even exponential relationships. We know when we take the inverse to try and understand things, we can use the log graph. So please remember these kinds of things and understand why we do them sometimes. Because these kinds of things, guys, will horrify you if you are not ready for them. They will be ready for you in the exam. That I can assure you. Even if it's not the exam today, an exam 5 years to come might haunt you if you don't understand your story. Okay, let's take a worked example and see how it can go for us. Okay guys, here's an example. We are told here that a willow, iwillow ke ngaba nithini ngumngconobe ngumngconobe laa mthi lowa ukhula emfuleni ufike amasebe wayo etshona emanzini. Yeah, that's a willow. Ngumngconobe. So ke kuthiwa apha umngconobe uyakhula ube ngumthi, right? A willow grows into a tree with a height of 2 meters. So this is the initial height in its first year. So this means this thing grew into 2 meters in the first year. Not a problem. Now its growth each year thereafter is 3/4 of its growth in the previous year. Okay, that means it will only grow by 3/4 of 2 in the next year, and 3/4 of whatever the result would be in the third year, and so forth. Now the question says, what is the greatest height it can reach? Okay, so can you see this is a geometric series? So let's see a solution to this problem is, we know that Sn is going to be 2 meters plus, now we take 3/4 of 2 in the next year, right? So when you multiply 3/4 to 2 here, what do we get? We get 6. Ne? Is it 6? No, that's 3/2 bafethu. Angazi why sengifuna ukubhayiza. Ne? This is just the growth of the tree, right? 2 times 10 endingazithembanga nje times 3/4 yam, and that's the 1 plus. Now we multiply this by 3/4 again to get the next growth. Dons. So we get 9/8, right? Of course, we need just 3 dons, and then we continue because we know this tree is going to keep growing, but you can see the growth is decreasing. As you would know, a human being grows, and then slows down until they no longer grow. You can also take a human growth example to express this. Now I'm going to something. Remember, even when you're doing microbiology, for example, you learn about why we are saying, certain things are going to be to the particular exponent, or we're taking a logarithmic what. Because you know that colonies can only grow into a particular habitat up until they no longer grow, because they will have exhausted the substrate anyway. So there can't be any further growth if there's no food, right? So we can almost estimate by how many times is this growth going to be if we were to place it into a much larger substrate where these things can thrive. This is looking at a human being. I mean, remember, we take a sample and send it to the lab. They will put it onto some agar media that is probably more like fitting a saucer, for those who grew up with grannies who drink tea on a saucer. Maybe they would fit it into that. And then, of course, they'll calculate the colonies they see there on a microscope. And then, of course, estimate how many colonies could they identify each day or each hour or what. And then from then on, we can see this thing and realize that, okay, it reaches a point where it doesn't happen anymore anyway, because the substrate is exhausted. So if they don't have food, how are they going to grow? It's not possible. How are they going to reproduce? It's not possible. Then we think of a human body now, and then we try, to estimate using the weight of the person. Of course, trying to use our known scientific data as to, under normal circumstances, what makes this bacteria grow, how much of it would be available in someone who has a weight of this sort. For example, let's say this thing is fastidious. It just wants glucose, and then how much glucose do we have in the human blood, for example, if this is a bacteria in the bloodstream? Stuff like this. So, of course, because I'm complicating a very simple question, but as you complicate. But do you realize what is this rate? This is the common ratio, because this is exactly the situation. So we know that R is basically 3/4. Now we know that the greatest height, this is nothing but sum to infinity, because we'll keep adding each growth to the previous growth up until it no longer grows. And then that would go to infinity, right? Because we cannot really determine exactly when will it stop. So that is sum to infinity. So this applies in certain situations like this. So we can easily say then S to infinity is going to be the height, or the greatest height. Maybe let me be silly now and put it like this. We can say then the greatest height is going to be the sum to infinity, which is A over 1 minus R. Even if we didn't write the formula here, since we are applying the thing, it doesn't really matter. So this is 2 divided by 1 minus 3/4. Let's see, what does it give us? 2 divided by 1 minus 3/4. We get 8. So this 3 can only reach 8 meters. Remember, this is the height of a tree, so there must be some things there. If you forget that unit of measurement, you lose the 1 mark for the answer, ne? Yes, of course. And obviously realizing that this is a common ratio, it's important. Sometimes you may get a mark there if you stated it. You may not get a mark, it doesn't matter. Because what matters is the correct substitution. And within this substitution, knowing that R is the 1, and then the answer, provided it has a unit, we could get our 3 fat marks in there. Of course, this one, it's a possible mark. If we got it, they will only get one mark for correct substitutions. But usually you would just get a mark for R, mark for the entire general substitutions, and the answer, provided it has M, because we're told the unit of measurement. If you forget it, you are dead, okay? So don't be careless. Remember, this is real life situation now. So you cannot just be careless about it. All right, guys, so this is one application of sum to infinity, and you can see it fits just right. Just right. Let's take one last one and end this pain. Okay, guys, so here is another one. So we can apply the sum to infinity to convert recurring fractions into some sort of proper fractions, or at least to show that those are rational numbers, meaning a fraction of integers, essentially. So this question is very rare in the exams, but I think in 2022, in the EC, it came out. So don't be caught pants down by things. So I'm teaching you these things so that you do not get caught pants down. All right, it's a very embarrassing situation when that happens. Okay, let's see. What is the solution here? We will see that, well, the sum here is 0,3. Right, that's the first one. plus 0,03. This is how the recurring fraction, remember, it's something like this. Plus 0,003 plus 0,003 plus, and then of course this goes on and on until Jesus comes. Remember, recurring fraction stops at infinity if we think about it. And you can check it, guys. Just start by saying 0,3 plus 0,03. Guess what? We get 0,33. And as we keep adding this, we get 0,3333333 recurring. This is something that is logical. Again, guys, we need to understand how to deal with these kinds of issues, because this is exactly the situation. Let me just highlight this in case you are wondering. 0,3 recurring is the same as 0,33333 until Jesus decides he wants to come back to punish us for sins or elevate us for our good, qualities and whatever. So if we break this down, we can say this is 0,003, because you see all these little things. This is what we can gather here. But now here is the very nice question, guys. The first thing that makes sense here is to convert these into fractions. Now, how many numbers do we have after the decimals? 1. So we take what is under the decimal and divide by 10. How many numbers do we have after the decimal? 2. We can just write 3. This is 0,3, but we're not going to write 0,3. This is the same as 3 over 100. Right? Plus, what is the story here? There's 3 numbers after decimal, but again, these are zeros. We just write 3 over 8,000. And you can even check again. You can take these into the calculator. You will see, you will get those back. Okay, so this is the same as 3. How many numbers after the decimal? 1, 2, 3, 4. So that's going to be 10,000. Right. So this is the thing. Again, you can check this out, guys. It must too can be checked. Is there such a thing? Yes, there's such a thing in my world. When I make it. So that's the one. It's just that it will write it in scientific notation in some calculators, but you can change that if you will. But this is the same thing, guys. This is plus. Now this one makes a bit more sense. Of course, you can still work with it using the decimals. It's not a big deal, but it's much easier when we convert this into some form of, proper fractions anyway. But now let's see, guys. Is there a common ratio between these things? Let's see. 3 over 100 divided by 3 over 10. This is the same as 3 over 100 times 10 over 3. The 3's take each other out. The 10 takes that. So our common ratio here is 1 over 10. Let's see when we say 3 over 1,000 divided by 3 over 100. This is 3 over 1,000 multiplied by 100 over 3. We can see the 3 still disappear. The zeros there, they will take the zeros. Again, we still remain with 1 over 10. So hey, it is clear that our common ratio is 1 over 10. So it's 1/10. So we know that R here is 1/10. We checked it. Now we can get rid of this thing. We can get it out of our system, because this should be done as a side calculation anyway. Showing the calculation is not impressive, isn't it? We can say, therefore, sum to infinity here is going to be A over 1 minus R. This is going to be equal to 0,3. Sorry, don't know why I'm writing it like this now. This is a fraction. This is 3 over 10 divided by angazi why ngibhala kakubi kanje, divided by 1 minus 1/10. Okay, now we can just go about it nicely. I mean, I just want to teach you something as well. So this is 3/10 divided by, we multiply 10 there, that's 10. 10 minus 1, that's 9/10. And then we're going to do this and say this is 3/10 times 10/9. No, what am I writing? Now 3 goes once, 3 goes 3 times, the 10s disappear. Guess what we have is 1/3. Yes, indeed. Yes, indeed. Of course, we used this as a means to an end. Now we need to show that, therefore, we know that 0.3 recurring is as good as 1/3. Nice and easy, guys. Nice and easy. Maybe let's use then here. Okay, sigqibile bafowethu. So if I will calculate 1/3 is 0.3 recurring. And we did it. We showed that this is a rational number because it's a fraction of integers. It is rational. You must know these things. You must know these things. Okay, guys, let's just cut the video here before it becomes too long. My intention is to try and push you guys to the end so that you don't just learn these things and you don't really see why you would need these at some point. These things can be very helpful in complex matters in maths, even for academic purposes, or even in real life applications, as you could see here. If we could just do an experiment. Now I push you now. Take an experiment, plant a maize, whatever. Faka nje wethu ikhozo lombona emhlabeni. Take corn. Is it corn? Umbona kuthiwa yintoni? It's corn, right? Take a grain of corn and put it in the ground. And then when it starts sprouting out of the ground, measure the length of that thing every day until it no longer grows. Right? Right. And then, of course, this is a real life situation. There may be other factors that can affect how fast it grows or what, because the sun is important as much as the rain is important. But of course, you will see certain things. I mean, there will be a lot for you to correct for this, but don't worry about the corrections. You will see that you may have to approximate certain things anyway. But you will see if it doesn't fit the sum to infinity. And in fact, the first 3 measures that you take, even though you're going to measure it until the end, then take the first 3 measures and try to calculate the sum to infinity, and then measure the actual length when it no longer grew. You will see that you will actually get very close, if not hit that number. And that's how nice it is to realize that certain things, they may look ridiculous as an abstract play or an idea, but actually in real life, you will see these things. You see, God was a mathematician, guys. Stop clowning around here. Anyway, I'll see you guys some other time. Goodbye. You will find this document in the description if you're interested in it. Cool. I'll see you when I see you. I'm out. And goodbye.